Hello, today's topic is on what is choke flow and how to apply that to feed system design principles. So, quick introduction. Many of you have probably seen this equation, m dot is equal to rho VA. It's your typical equation for conservation of mass. And we see, just by interpreting the equation, we can say that theoretically we could increase m dot infinitely by increasing velocity. However, in real world, because density changes with velocity due to compressibility effects, that is not the case. So, for more details on the definition of compressibility compressible versus incompressible, there's another video that kind of goes more in depth. But the main takeaway for that is if you just look at the graph on the right, this plots the density of oxygen at different temperature and pressure conditions. The main takeaway when you look at this graph, or kind of the idea of understanding compressibility, is that your density of that fluid is subjected to change based on different pressure and temperature conditions. And that is an important thing to understand because that is kind of the whole idea of choke flow and why choke flow is valid. So, okay, what is choke flow? I think it would be most useful to think of it like a special condition. So whenever something is choked, we mean that, let's say that in the case of a CD nozzle, so conversion diversion nozzle or de Laval nozzle, we say a choke flow occurs when the throat, and we define throat as the minimum cross section area in that system reaches Mach 1. And in this special condition, in this choke flow condition, your mass flow is maximized in the sense that no matter how much you increase the change in pressure between that orifice, your downstream properties no longer matters, and no matter what your flow rate, because it's choked, is not going to change unless you change the orifice size. And this applies to single phase only. And when I say that, I mean since we're working with mostly nitrous oxide, we won't be able to apply the same equation for nitrous. For nitrous, we would use something like HEM, NHEM, and we'll go over that in more details on another video. But for choke flow, there are two main equations that you need to know. Well, the first thing is you want to know what the choke criterion is, right? You want to know under what conditions your flow is actually choked. And a very practical way of doing that is to see how the ratio of your upstream pressure, ratio of your downstream pressure over your upstream pressure compares to that choke criterion. And then if you do satisfy the choke criterion, so your ratio of downstream to upstream is lesser than that choke criterion, then your flow indeed will be choked. And so if it satisfies, you can then come down here to use that equation and solve for maybe m dot or throat area depending on your application. But today we'll be talking about kind of how to use it to solve for the orifice size, which is your throat area. So going over more these equations in more details, the choke criterion is mainly the term on the right. So and it is a function of your specific heats, and that is the value you can find using NASA CA-Run or NIST. And then your PD is your downstream static pressure, and your PT is your upstream total pressure. So you compute your choke criterion, and then you look at how the ratio of your system compares to that. If it's lesser, then yes, your flow is choked, and if it's not, then no, it will not be choked, and the equations on the right will no longer apply to your application. So now let's say that today your flow is choked. How do I actually apply the equations on the right? Okay, so we see that m dot here is a function of CD, discharge coefficient, throat area, your total pressure, your gamma, and your temperature, and then the ideal gas constant. Typically at PL, we use this equation when we want to solve for the orifice diameter or the orifice area. So in this case, we just have to rearrange the equation on the top to solve for AT. We just plug in everything here that we just plug in all the constants, and then we solve for AT. And that should basically tell you the area of the orifice, and you just have to solve for your diameter using pi r squared. And you should be able to get something off like McMaster's or Titan Fittings. Actually, I'm not sure if they sell orifices, but yeah. And if you want to, that's kind of how you use these two equations. Just always remember to always check for choke criterion, because you might not satisfy. If you don't satisfy choke criterion and you're using the equation for choke mass for compressibles, then your values are bound to be wrong when you calculate them. And this is a derivation. If you're interested, there's also a lot more papers on like the whole details and testing of that relation, if that's something you're interested in. But yeah, just let me know if you have any more questions.